Well, hey, students, it's Mr. Harrison here for school. Uh, got your screencast of 5 video for your atomic history um, assignment in Canvas. The title of the slideshow is called the Atomic Structure Timeline, and it just provides you a general history of the atomic theory, which is what we're talking about. And never mind about the sheet, we're using it to complete the Canvas assignment instead. So let's get going. Our first scientist is called Democritus, who was approximately 400 years BC. Give or take a few years, it was in that ballpark. He was the first person to propose the idea that matter is all composed of tiny, indivisible particles. Don't confuse this word indivisible with the word invisible, which means you can't see them. Although you can't see them, they're too small. Indivisible is the same thing we say in the pledge, and it means undividable. It wasn't really based on any experimental data. It was just based on kind of just logically thinking it through. And he's the first person to come up with the name atomos, which means it's in Greek, and it means atomos, which means undividable. Then for about 2,000 years, we stubbed our proverbial scientific toe trying to turn cheap stuff into gold in a practice called alchemy. And it's a mixture of science, terminology, and mysticism. It's what's considered a pseudoscience, which means it has the appearance of science, but it really isn't science, although it uses some of the equipment. Essentially, what we're doing is trying to turn less expensive metals into gold. If you remember the story of Rumpelstiltskin weaving thread into gold, it was sort of like that, but with metals. And we tried and thought maybe we were successful with certain things, but in truth, it was an utter failure. And there's a reason for that. And it was because Democritus was correct. And gold is actually an element. So you can't turn anything into gold. It needs gold atoms to do that. So fast forward almost 2,000, actually about 2,500 years almost. John Dalton enters the scene around 1807 or the early part of the 1800s. He was a school teacher in Britain, and he didn't actually do any experiments. He just based his theory on the experimental data of other people. The name of John Dalton's model of the atom is called the billiard ball model. If you've ever played billiards or like pool, not as in pool like a liquid container, pool as in like pool cues and trying to put all the balls in the pockets and stuff. That's called, the actual name of the game is called billiards. And so he said the atom is a uniform solid sphere, much like a billiard ball. And he also came up with 4 ideas, which he called his 4 postulates in terms of atomic theory. And you could think of him as the kind of the father of atomic theory in general. Here's his 4 postulates. Number 1, elements are composed of small, indivisible particles called atoms. So basically, he just confirmed with that one what Democritus thought. Then a second postulate, atoms of the same element are identical, and atoms of different elements are different. In other words, he's saying that the atoms themselves are what makes them different. His third postulate said that atoms of different elements combine together in simple proportions to create a compound. And he came up with the idea that it might be fixed ratios of those proportions. And his fourth postulate was that in a chemical reaction, atoms are simply rearranged, but they're not changed into anything else. And all 4 of these generally hold completely true even to today. Then fast forward almost 100 years, we've got J.J. Thomson. And you see up here, there's no P's in his name. He's missing the P in Thomson. Not really, that's just how his name is spelled. But I use that to remember the name of his model, which we'll get to in a second. His experiment that he used for J.J. Thomson was called the cathode ray tube experiments, where he shot a beam of negative particles, and those negative particles that he discovered through the cathode ray tube experiments were called electrons. So he basically discovered electrons, which are negative particles within the atom. And he called his model the plum pudding model, which has two P's in it. Remember, his name was missing the P, so he made up for it and overcompensated and put 2 in his model. JJ, no P's, came up with the plum pudding model. Another teacher also uses a little bit of controversy and says she remembers it by saying JJPP. Whatever works for you, doesn't matter to me, however it sticks in your head. But his model is called the plum pudding model, and that's because at that time in the early 1900s, there was a food item that they would eat, usually for a side and often for dessert, called plum pudding. And it was a bunch of like doughy stuff with little speckles of like sprinkles of bits of plum in them. And he said that the atom is like that. It has a big doughy area with the, not really doughy, but like the dough in plum pudding. And then there's sprinkled in electrons like the plums in the plum pudding. And it looks something like this. You've got a positive sphere. So the whole billiard ball sphere shape is positive. And then you've got negative electron plum-like things sprinkled or dispersed throughout. Positive sphere with negative electrons dispersed throughout. And then fast forward a few more years. This is in the same general time frame. We've got Ernest Rutherford. And he did an experiment called the gold foil experiment, where he essentially shot particles, very microscopic small particles, at very, very, very thin gold foil. And he expected that all of them were just going to go right through the foil because they're very small, smaller than an atom. What he found is that most of them went through the foil, but some of them were deflected. And some of them even deflected and bounced almost directly backwards back towards him. So what he discovered is he discovered the nucleus of the atom, which is a dense positive charge in the center. He didn't know about anything in the nucleus. He just knew that there was a dense positive nucleus in the center. So his model was called the nuclear model. And the way that I remember that is Rutherford has a U, so does nuclear. It's actually pronounced Rutherford, but I say Rutherford was the nuclear model, even though it's mispronouncing his name. Here's what the nuclear model looks like. You've got positive, the positive center. You could argue he discovered the proton. He wasn't sure what it was. He just knew it was positive. And then you got the negative parts, the electrons are on the outside. So the two subatomic particles that he knew about were the proton and the electron. You could argue that Thomson from before just knew about the electron. Dalton didn't know about any of it. But he said that his model, the nuclear model, has a dense positive nucleus surrounded by negative electrons. Then, almost exactly the same time, about 2 years later, Niels Bohr came onto the scene, and he did an experiment called the bright line spectrum experiment. And he's trying to explain the presence of specific colors in the atom or the element hydrogen spectrum. And through this experiment, he discovered that not only are electrons around the outside of the atom, but they exist in specific energy states. And his model was called the planetary model. And you're going to have to yawn to do this, but I remember this by thinking that planets are boring. Niels Bohr, boring, planets. That's why it says planets are boring here. Here is his planetary model. This is the one that you probably recognize. I think the show The Big Bang Theory has this kind of model. It's a very common model because it's very practical, even though it's not quite accurate. It's very useful. So again, it was the bright line spectrum experiments. It's called the planetary model. It looks like this. When you draw it, you might have to look at that. And it's got electrons that move in circular orbits with specific energy levels, very specific, predictable patterns. Then we move on to Erwin Schrödinger. And his experiments that he used weren't so much like actual physical experiments as much as like mathematical thought experiments. And he employed a method of thinking called quantum mechanics, which is just super cool, nerdy science term. Quantum mechanics is like a predictability, probability kind of analysis. And he said, yes, electrons can only exist in specified energy states. And he came up with the electron cloud model because he said that the electron orbitals, as he called them, are not necessarily fixed orbits. Like back here, our old buddy Bohr said that they go like planets around the sun in fixed orbits. He said, no, he's onto something. They have specified energy states, but they're more like those energy levels are more like probabilities. In other words, it's not specifically where the electrons are, it's where they're likely to be found. He said you can't actually predict exactly where they're going to be. You just can predict the range that they're likely to be found at. And he called those orbitals because he's like, they're not really orbits. They're more like orbitals. They're like general ideas. They're not very specific. And his model looks crazy. It's got a bunch of polka dots. And you can see kind of an area right here where it's more dense, and then like right here it's less dense, and then it almost looks like they're on the edge. It gets a little more dense again. Those dots represent the probability of finding an electron. By the way, when we write E minus, that stands for electron because electrons are negative. So we just write it E negative. Again, the dots represent the probability of finding an electron, not actual electrons themselves. And then we got James Chadwick, who was about 15, 20 years later. And just to simplify, James Chadwick discovered that there's neutral particles in the nucleus as well as positive portions. So he discovered the neutrons. And the neutral particles are in the nucleus with the protons. And he used a lot of the data from the Joliot-Curie experiments. That's Madame Curie. She ended up dying because of radiation poisoning, but he used some of their experimental evidence to come up with his idea. So here's his model. Pretty similar actually to Thomson's model, J.J. Thomson, the plum pudding, except instead of having a positive sphere with the electrons sprinkled in, he had a dense positive nucleus that also had neutral particles. So he knew about the proton, the neutron, and the electron. And it was essentially also a revision of Rutherford's nuclear model. So you could either have it like the plum pudding with the electrons sprinkled, or I'll walk you back here to Rutherford's nuclear model. Dense positive nucleus. It's kind of a combination of those, but it's probably more like the nuclear model because it has the positive nucleus in the center. And that's our last guy. So just to review, James Chadwick's model is called the neutron model. It looks like this for your drawing purposes. He discovered the neutrons. Then you got Schrodinger's model, which is the electron cloud model, and it looks like a cloud of electrons. Then you've got Niels Bohr, which is the planetary model with the fixed orbits like planets around the sun. And Ernest Rutherford's was the nuclear model with the dense positive nucleus in the center and the electrons are on the outside. And then Thomson's, which is the plum pudding, positive sphere with the negative electrons sprinkled all throughout. And lastly, Dalton, which was the billiard ball model, just a sphere. Hopefully that helps. You can go ahead and move to the to answer the questions and to fill out your the 2 Canvas quizzes that go with this.